Welcome to the Explainer. Today, we're unpacking a truly fascinating journey. We are going to dive into the exact evolution of how artificial intelligence actually learned to process images, using the exact same technology it uses to process text. It is a story of incredible engineering, super clever problem solving, and massive leaps in computing power. And all of this ultimately led to the tech that is secretly powering everything from your phone's image search to modern self-driving cars. Okay, let's just quickly glance at our roadmap for today. We're covering fueling computer vision, the core vision challenge, our first attempt with image GPT, the huge breakthrough of vision transformers, and finally, efficiency with DEIT and MAE. Let's get right to it. Section 1. Fueling computer vision, the datasets that built modern AI. Just look at this massive escalation. To understand the engine, we first really need to understand the fuel, right? In the early days, researchers relied on MSIT, which was basically just 70,000 simple 28 by 28 pixel grayscale images of handwritten digits. Then came SciFar, bringing 60,000 32 by 32 color images across specific classes, like birds, cats, and airplanes. But the true game changer? That was the ImageNet project. We're talking about more than 14 million hand-annotated, high-resolution images. To put that into perspective, if you looked at one image every single second, it would take you almost 6 months of nonstop viewing to see them all. It was AlexNet's use of this colossal dataset back in 2012 that really kickstarted everything we have in modern computer vision today. Moving right along to Section 2, the core vision challenge, speaking the Transformers language. And this brings us to a really fundamental puzzle. You see, transformers became wildly successful in natural language processing because they are incredibly good at reading text. And text is inherently a one-dimensional sequence of words, just one right after the other. But an image? An image is a flat, two-dimensional grid of pixels. So the ultimate question researchers faced was this: how on earth do we translate a flat 2D picture into a simple 1D sentence that a transformer can actually read? This brilliantly illustrates the original Transformer engine. You can see the full, complex architecture there with all its multiple blocks. But remember, to process these new image sequences, vision transformers actually stripped this down. Instead of using the whole shebang, they only utilize that encoder block you see on the left side. The encoder is entirely responsible for transforming those input images into a sequence of tokens and learning the spatial relationships between them. Section 3, First Attempt, Image GPT. OpenAI's Pixel Push. So, with the encoder ready to go, how did researchers first try to force an image into it? Well, the first major attempt to solve this translation problem was OpenAI's Image GPT, and they took a very brute force approach, right down to the individual pixels. To force an image into a 1D sequence, Image GPT had to drastically reduce the context. Let me frame this for you. A standard ImageNet picture has a resolution of 224 by 224 across 3 color channels. That is over 150,000 pixels. To make it work, ImageGPT had to crush that rich, detailed image down to a measly 1,024 pixels. That's literally a lower resolution than most video games from the 1980s. This severe context reduction required a drastic 3-step pre-processing phase to strip down the visual information before the AI even looked at it. First, they reordered the pixels to create a flat sequence. Second, they resized that massive ImageNet image down to an incredibly low 32 by 32 resolution. And third, they customized the color palette, totally abandoning full RGB to compress it into a single dimension. Now you can visually see the massive sacrifice required for this brute force method. Check out the first image, a detailed, high-resolution picture of a white dog. Now look at the second one. Because of that extreme downscaling and color restriction to just 1,024 pixels, the dog gets abstracted into this highly simplified 9-color palette block. It barely even looks like a dog anymore, does it? But it was completely necessary just so the model could process it as a sequence. Once they finally had that simplified sequence, they used a GPT-2 architecture and trained the model using one of 2 primary objectives. First, the autoregressive objective simply asked the AI to predict the very next pixel in the sequence, kind of like predicting the next word in a sentence. Alternatively, the BERT objective challenged the AI to find a matrix to predict a hidden or masked pixel somewhere within the image. It's like playing a visual game of fill in the blanks. But as we just saw with the dog, this pixel-by-pixel method had some really severe limitations. Which brings us to Section 4, Breakthrough Vision Transformers, Google's patch innovation.
Because ImageGPT was losing way too many crucial visual and structural details by crushing everything down to that tiny 32 by 32 size, it paved the way for Google to rethink the problem entirely. This led to a massive breakthrough. In 2020, Google published a paper with this iconic title that gave us the definitive answer. An image is worth 16 by 16 words. The core realization here was simple but absolutely profound. Stop looking at individual, heavily compressed pixels and start looking at localized patches.
So here's how it actually works. The Vision Transformer, or VIT, takes the original, high-quality 2D image and literally chops it up into a grid of tiny 16 by 16 squares. It then flattens those patches and feeds them right into the Transformer encoder. It is quite literally treating each distinct visual square as a single word in a sentence.
And the difference in performance was staggering. While ImageGPT lost structural detail and was capped at a super low resolution, VIT's patch method retained the essential spatial structures of the image. By treating patches as tokens, VIT was highly successful and officially outperformed the traditional convolutional neural networks that had basically dominated computer vision for years.
Finally, Section 5, Efficiency. DIT and MAE, making AI faster and cheaper.
Okay, so we had a working, highly capable model, but there was a catch. The original Vision Transformer had a major flaw. To get those incredible results, it required a massive, completely private dataset for training. This meant most researchers couldn't even replicate it. Facebook responded to this by creating DATE, the Data Efficient Image Transformer. DATE proved that you didn't actually need a closely guarded data vault. You could achieve incredible transformer results using the standard, publicly available ImageNet database, which was 10 times smaller than what VITE initially used. But the ultimate efficiency breakthrough, that came with masked autoencoders, or MAE, which introduced an asymmetric encoder-decoder architecture. Its absolute genius lies in its self-supervisory task. It deliberately masks or hides a remarkably high proportion of the input image right from the start. This forces the AI to learn the underlying patterns, much like a human completing a jigsaw puzzle with missing pieces. Let's actually walk through this genius workflow step by step. First up, they sample a subset of the image patches and completely mask out the rest. Second, the VIT encoder only takes in and processes the few patches it can actually see. Third, they add positional data and mask tokens, which are essentially learned placeholders for the missing pieces. Fourth, a decoder takes all of this and tries to guess what the missing image patches should look like. And finally, the output is reconstructed, and the AI grades its own homework by calculating the mean squared error between its prediction and the original hidden image. Because the heavy, computationally expensive encoder is only processing a very small fraction of the image and completely ignoring the masked portions, the efficiency gains here are massive. Training speed increased by a staggering 2.8 to 4.1 times. This meant researchers no longer needed supercomputers just to experiment. It made training powerful vision transformers faster, cheaper, and vastly more accessible to the rest of the world. From parsing 28-pixel handwritten digits to chopping up high-resolution photos into sentences, the journey of the Vision Transformer shows just how adaptable and incredibly powerful this architecture truly is. Which leaves us with a fascinating final thought for this explainer. Now that we've optimized how machines translate pixels into a language they perfectly understand, what groundbreaking realities will they build with it next? Thanks so much for joining me on this deep dive, and keep your eyes peeled on the future of vision.